In this lesson, we'll discuss the univariate models of prediction and forecasting with the help of our ARIMA class of models. We'll start with the concept of time series stationarity and white noise process. Then we introduce autoregressive AR processes and their structure with the help of a simple example. We also discuss its stationarity property. We'll also discuss the autocorrelation coefficient and autocorrelation function and partial autocorrelation function in the context of AR processes. Next, we introduce the moving average or MA processes and its structure with the help of simple example. We also discuss the ACF and PACF plots for an MA process. In this video, we'll discuss univariate models of prediction and forecasting. Univariate time series models of prediction and forecasting are an extremely important class of models. They are specifications where one attempts to model and predict financial variables, in particular, for example, financial market prices, using only the information contained in their own past values and possibly current and past values of an error term. We'll have more to say about this error term, but generally this is used to mean or denote the information that has just arrived in the market. Unlike the structural models that include some theoretical underpinning and a number of variables, these time series models are atheoretical, such as modeling high frequency trading data. What do we mean by this? In general, any such model would derive or take away from some kind of structural model. However, we do not care what that structural model is as long as we have the variable of interest such as security market returns and its own past values. It is assumed that any such structural model that we do not observe or know about at play, automatically that information that is contained in that structural model is incorporated in the historical time series values of the variable of interest. So for example, you may have some idea that GDP of a country may affect the returns of Nifty 50. Let's say Indian GDP affects Nifty 50 returns. Even though I may not have the knowledge about this model, but I know as long as this GDP affects Nifty 50, and I know that as per the time series model, the historical values of Nifty 50 will help me predict the future values of Nifty 50, I can be rest assured that this relationship, this underlying structural relationship will be captured while I model this time series model of Nifty 50 with its own previous values in time series model, which is rather more atheoretical nature, but by this background, it automatically incorporates the information content of the structural model, which incorporates the relationship between GDP and its impact on Nifty 50. One of the most important class of such models includes autoregressive integrated moving average ARIMA class of models. We'll have more to discuss about this model. Why such time series models are important, and particularly the univariate models, is because often when you are modeling the financial market data with modern financial market instruments that are part of this course, structural variables are not available at high frequency, and most of the modern day trading is happening at high frequency domain. So whenever you are modeling any such model where high frequency trading or any such relationship on daily or weekly basis where more structural variables are not available, such as GDP or central bank policy variables, then you have to rely on the historical values of the variable that is available, for example prices PT or returns RT, that are available on higher frequencies, and you have to rely on such time series model that employs past values of the variable itself. This is one important motivation of using these time series models. To summarize, in this video we discussed the importance of univariate time series models. We noted that in modern financial markets, the trading activity and various other dynamics play at extremely high frequencies such as intraday level, where various structural model variables such as GDP and monetary policy variables are not available at those frequencies, and therefore we have to rely on the historical values of the variable itself such as returns and prices to model the data using models such as ARIMA models. And therefore, in this condition, the univariate time series models for prediction and forecasting becomes an extremely important class of variables. And even more so, it has been found that while examining the prediction accuracy through methods such as out of sample prediction, these univariate class of models often work even better than the structural models as well. And also the data requirements of these models are extremely parsimonious and they are extremely easy to model, and that provides us the intuition and motivation to work with these and learn these univariate time series models. Introduction to time series stationarity. In this video, we'll discuss weak and strict form of stationarity and also the problems that happen when we employ non-stationary series. Let's start with the strict form of stationary process. In a strictly theoretical sense, a time series process xt is said to be strictly stationary if the joint probability distribution of sequence of yt1 to ytn is same as that for yt1 plus m to ytn plus m for all m's. That is, the joint distribution of yt1 to ytn is same as yt1 plus m to ytn plus m. That means as long as we have the distribution of observations, the different movements starting from first movement, that is mean, second movement which is change, or second movement which is sort of, you can say, variance, and higher movements are same across as the time progresses across all the observation. For example, whether you are looking at from yt plus 1 yt1 to ytn, or m steps ahead or k steps ahead, the set of observations that you have, its joint distribution for a given set of observations remains same. Or put it more simply, for any observation, if I pick for any time tk, if I pick observation yk or ytk, the probability that it will lie in certain interval will remain constant as time progresses. This is called stationarity, strictly stationary process, which has a lot of desirable properties. However, in a practical sense, we make use of something called weak stationary process. What do we mean by weakly stationary or covariant stationary process? We mean the following. This kind of process has the constant mean, that means the first moment, which is the mean, it is constant. Second moment or variance is also constant, sigma square. So the variance is also constant, which is the second moment, expected value of yt minus mu into yt minus mu. And also the autocorrelation structure, that means correlation of a yt with its own previous values is constant. That means whether you are looking at y correlation between time t1 to t2, that is yt1 to yt2 or yt1 yt2 to yt3, what is important is what is the difference between those time periods. For example, t1 to t3 or t3 to t5, the correlation expected to remain same. So what matters only is the time gap between them. For example, if the time gap is 5 lakhs or 6 lakhs, it is what only matters. It doesn't mean what time you are standing. So you can compute the autocovariance for a s lag period like this, expected value of yt minus mu into yt plus s minus mu. This is for s period difference, so this is for s lags gamma s, and this autocovariance structure remains constant as time progresses. While this is an important measure, because of scale across different processes is difficult to compare. So what we focus on is called autocorrelation. That means correlation, which is a standardized or normalized version of autocovariance. So if you divide the autocovariance at different lags, maybe lag s, where s can be 0, 1, 2, with autocovariance at 0 lag, that means autocovariance at 0 lag is variance itself. That means autocovariance with its own term, which is essentially nothing but gamma naught, which is variance. This scaled version, this scaled value is called autocorrelation. So at s equal to 0, this value will be 1. In general, this value varies from -1 to +1, and this autocorrelation value, it measures from -1 to +1, and an extremely important measure to define a weakly stationarity process, the autocorrelation structure of a weakly stationary process. So if you plot this autocorrelation on a graph starting from 0 lag, first lag, and so on, at 0 lag you get a value of 1, and next whatever autocorrelation structure is there, you can plot this at different lags 1, 2, and 3. This kind of diagram is called autocorrelation function, autocorrelation function, ACF, or in short ACF diagram, which we'll be using very heavily, and it is also called correlogram. So this will be called correlogram or autocorrelation plot or ACF plot. So let's discuss what are the problems of working with non-stationary series. Like we've defined, the non-stationary series is a series where different movements do not stay constant with time, particularly the first movement, which is mean, the second movement, which is variance, and the autocorrelation structure tau s does not remain constant with time. Such non-stationary series has various problems while working with them on econometric estimation. For example, shocks to such non-stationary series do not die away. A very desirable property of any economic series or econometric series, time series, is that any shock dies away naturally over as time progresses. However, for non-stationary series, because of their trending nature and drastically varying different movements, the shocks to the series do not die away and they are highly persistent. This is very important point. The second important point is that estimation with non-stationary data can lead to spurious regressions. For example, even though the two series, maybe y1 and x1, they are not very related, but still if you run some kind of regression on them, they appear to be very spurious, resulting in high t statistics and adjusted r square. For example, if you sample from two non-stationary series and two different period samples and keep on sampling the process over and over and run regressions, you will find a large number of adjusted r square like plotted here, a very high values for the sample adjusted R square, and also very high t statistic values, which should not be the case. Ideally, if the two series y1 and x1 are independent, any sample and subsequent regression should give you poor adjusted R squares and t stats. But because of this trending nature of non-stationary series, for example, non-stationary series, the shocks to the system do not die away, and therefore they appear to be moving or trending like this, the y1 and x1. So because of this trending nature, at whatever point you take a sample, y1 dash, x1 dash, or y2 dash, x2 dash, they are always trending. And this results in some kind of positive or negative spurious relationship when you estimate some kind of correlation or regression measure on them. To summarize, in this video we discussed a strict stationary process and a weakly stationary process that is often employed in a practical sense. We also saw some of the shortcomings and problems with estimation of these non-stationary series with econometric methods such as regression. In this video, we'll introduce white noise IID, or identically independently distributed process. We'll also understand what is the importance of modeling a process as white noise process. To begin with, white noise means a process which has no discernible structure. To put in more detail, a process with a constant mean, generally that mean or expected value is taken as 0, but it can be a constant number. We generally take it to be 0, and a constant variance sigma square, which is not changing across the process because there is no discernible structure, or there is no reason to expect that this sigma square or variance of the process will change. But most importantly, there is no autocorrelation or autocovariance structure. That means for any two values in the process, this T1, T2, they need not be immediate preceding term. They can be any two values taken from a time series of values, maybe T1 to T3 or T1 to T2 or T1 to Tk, any such two generic values, the correlation or covariance between them is 0 for different values of T1, T2 and so on, where as long as T1 is not equal to T2. If T1 is equal to T2, then this becomes variance or sigma square, and in autocorrelation terms, this value tau 0 will be equal to 1, as we have already seen. So to put or summarize this, we are saying a white noise is a process which has a constant, or rather 0 mean, a finite constant variance, and it is not correlated across time, that there is no autocorrelation. Sometimes you also put some assumption about the distribution, and generally this is a normal distribution, so this becomes a white noise normal IID process. That means when you say independently and identically distributed, that identical distribution is normal, so in most of the cases. But a more generic term is IID, which where one I is for identical, another I is independent, and D is for distribution. So a normally distributed white noise IID process is a special case of white noise process. Now, just to summarize this, what is the importance of modeling a process? Or when I say process, it can be financial market returns and so on, as a white noise IID process. Many times you model the prices given a certain model. It can be various advanced models, as we'll see, like Garch kind of model, Arima model in this case. But once you model it, you tend to believe now that you have taken out everything, every discernible structure in the process and modeled it. So if you have modeled it correctly, the residual or error term in the process after you model the series, let's say you're modeling return series, you model out with some kind of ARIMA process, a generic term, and extract the residuals from the model, let's call them muties, then the assumption here is that if we have done everything correctly, these residuals that are extracted from the ARIMA process should have no discernible structure, because if we have modeled correctly, any discernible, any kind of pattern that should be modeled is modeled through parameters of this ARIMA. So in the residuals or the remaining part, there should be no discernible structure, and therefore it is argued that this muti or error term should be as close as possible to a white noise IID process with no discernible structure. And that is why it is very important, once you model a given process or return or financial market series, a time series model, then you make an assumption about residual being white noise, and then you test the residual for white noise, and that testing of white noise residuals is a sort of verification of your modeling accuracy or how good your model has been. So to summarize, we are saying that a white noise process is process with a constant, generally zero mean, constant variance, and no autocorrelation structure, no discernible structure. Generally, we use such modeling through white noise. We model residuals from an ARIMA class of model or any other similar model, where the assumption is that there is no discernible pattern in the error structure because we have modeled out anything possible in our model efficiently. So generally there should be no discernible structure in our muties, or put it more specifically, there is no autocorrelation structure in our muties or error terms. If there is, then there is some problem with our model. In this video, we'll introduce the AR or autoregressive process, which is a very important component of ARIMA. So this AR in ARIMA stands for autoregressive process. We'll also discuss the motivation for modeling a process through autoregressive process. To begin with, autoregressive or AR processes assume that a time series process YT depends on its own previous values. The structure of AR model can be given as follows. So let's say you assume an ARP process where P indicates the number of lags. For example, a process YT is modeled with a constant term mu plus its own previous values yt minus 1, yt minus 2 up till yt minus p, because this is a p order process, and therefore the coefficients of these yt minus 1, that is phi 1, phi 2, run up to phi p. So this is a ARP process because it is affected or it is modeled at its own previous p lags. This muti is error or innovation term. Now, this can be further simplified by writing yt in a more compact notation by summing up all these p terms into this p notation summation I equal to 1 to p phi I into yt minus I, where I runs from 1 to p. Moreover, we can use something called lag operator, where lag operator Li on a process yt means yt minus I. So a lag operator with a subscript I would mean y series with a lag I. So this term can be further simplified with a lag operator like this. We'll see later what is the importance of denoting a process like this. Again, muti is the error term. This muti can be written as a white noise. This is assumed to be a white noise IID term. Ideally, if the process is purely an AR process, autoregressive process, and we have modeled it appropriately, then muti should be purely white noise. Generally, we put another assumption of normality. So it is considered to be distributed as normally distributed with a mean 0 and constant variance. Once we have modeled this process in this form, we can take out this phi I, this particular part on LHS, and therefore the left side becomes some kind of function of YT series with phi L, where phi L denotes these set of parameters. So the sample space or the sort of parameters that are part of phi L are these phi 1, phi 2 and so on, and lag operator indicates that this is applied with a lag. So yt minus 1, yt minus 2 and so on. Or to put it more clearly, now phi L here would be 1 minus phi 1L minus phi 2L 2, or L square. You can also call it L square. Later we'll see the application of it, minus phi p LP. So this you can call as LP or L to the power P. Now, why I'm using the word L to the power P? Because often when you characterize this AR process, this is called characteristic of equation of this AR process. I repeat, this is called characteristic equation of AR process. And on LHS we have this phi L YT function, where this is the phi L YT function. On RHS we have the constant term. Generally in financial market, when you are modeling financial market returns and those kind of financial market process, this mu tends to become 0 often, sometimes it's not. And mu t is this white noise IID error term, which is normally distributed. Now later we will see that in algebra, the roots of this characteristic equation are very important to understand this AR process. So often these roots are very important in determining properties such as stationary and non-stationary AR processes. So this characteristic equation becomes very important, and therefore these subscripts become powers. For example, this L1 become L to the power 1, or lag operator at second level L2 becomes L square, and then this will be solved like any algebraic equation. So this is become those similar algebra kind of problems where this equation is called characteristic equation of this ARP process, and its root, which will be very important to this process, which will be used to define the properties of this AR process, are employed. Now, in summary and conclusion, we'll try to understand what is the motivation to model a process like this AR autoregressive process. Process in financial markets like AR, it is often believed, and for that you need to read a little bit of financial market literature like sequential information SIH, sequential information arrival hypothesis, mixture of distribution hypothesis, and information asymmetry hypothesis, that as information arrives in financial markets, in first place, complete information never releases in one go. So information itself is released in a piecemeal manner in chunks of information pieces like delta 1, delta 2 over time. And as these information pieces arrive, they are not immediately incorporated in prices. It takes some time. So this arriving information, or the information that has arrived, incorporates gradually over time in financial market prices. And therefore, by nature, this in first place, this information is auto-correlated because it is being released in the piecemeal manner, and also because it is being gradually incorporated in prices. By design, there is an auto-regressive structure in financial market returns. That is to suggest that financial market price returns are auto-correlated, and that is why theoretically AR process becomes extremely important to model financial market returns. The significance of this muted term is also very important. In econometrics or in modeling statistics, this is often treated as error term with not much value, error term or innovation term. However, in financial economics, this muti has a very important role. Generally, it is considered that when you model this muti, this is taken to be as the information shock or innovation or information shock that has just arrived at time t. So it is believed that once you model out the previous historical information structure which has been auto-correlated, like I said, information is arriving in a piecemeal manner, so it is bound to be auto-correlated. Once you model out this auto-correlated information, what you are left with an information shock which is completely unexpected. So this muti is unexpected information shock, and this information, the information shock has no information content in the previous process. So this is unexpected. Had it been the case that some of this information was already understood or explained by the historical terms, it would have been modeled out. So whatever left unmodeled in this muti is called unexpected information shocks to this YT process. And that is why modeling these financial market processes such as returns, it is extremely important. The AR becomes theoretically extremely important process. One last point, very important point, that often some kind of statistical model may give you a very good fit, which is not an AR. However, that model may not be theoretically justified. So always remember, in modeling financial market and financial economics or any kind of economic series, theory is given preference over statistical and goodness of fit. So even if a mathematical model is giving a very good fit, but it is not theoretically justified, we should not use that. We should use a model which is theoretically justified. This is important because ultimately you are trying to model this process from some policy perspective. Maybe you want to do some kind of policy experiment. Maybe you want to look at the impact of GDP on financial market index returns like Nifty 50. In that case, theoretical relationships are important. And even though we are using time series process, but still a theoretically justified structure is very important to have. And the second implication of that is often such mathematical models, good models, which work very well in sample, when you model them out of sample in new data, they work very poorly In contrast, a model which are theoretically justified, which have some theoretical underpinning, even though their in sample fit in a given sample in they were modeled, may not be as good as some kind of very complex mathematical model. When you look at out of sample fit, these models generally work. These models which have some theoretical underpinning, they work much better than any statistical model which may not have some kind of underpinning and maybe a complex model as well. In this video, we'll discuss the stationarity of an AR process. Stationarity for an AR process is very important. We have already discussed that what are the problems with a non-stationary process. Also, if an AR process is non-stationary, that means the impact of some of the previous values on some of the current and future values do not die away. What it essentially means, if there was a shock historically in a system, it does not die away and it persists for very long times, which is not very desirable property in modeling any such AR or ARIMA-ARMA process. Let's understand what is stationarity mathematically. Recall, we said an AR process will appear like this, where phi L by T is autocorrelation structure, represented by this kind of structure where phi L is 1 minus phi 1L, phi 2L square and so on. These phi i's are essentially autocorrelation coefficients and this L is lag operator. For example, if it is written as Li essentially at Yt, it is essentially Yt minus I. And in lag notation, conversely, this can also be thought of as some kind of polynomial in Z, and later, as we have already said, this is like a characteristic equation, a polynomial in L. So you can think of this Li as L to the power I also. As we'll see, this needs some understanding of Vol's theorem. The second important point here to understand that this mu is some kind of constant term and mu t is that error or innovation or information shock. For modeling financial market data such as financial market returns, we take this mu as 0. Generally it is considered to be 0 in financial market process such as return for the following reasons. If this mu takes on some kind of positive value, that means there is some kind of arbitrage to be made to make excess abnormal returns, and if it is negative, vice versa, that is short positions can be taken to make abnormal returns, and therefore on average this mu should be insignificant or close to 0, and that is why a more practical assumption is to take this as 0, which means now phi L by T is equal to mu T, that is phi phi operator on by T equal to mu T, or with the Vol's theorem we can write phi T equal to phi L inverse mu T. Now this kind of transformation, taking inverse of this phi L, is possible because of something called Vol's theorem, which is out of the scope, but the point is, for this kind of transformation to exist, it is needed that phi L be a stationary function. That means this equation must represent a stationary process. What do we mean by stationary process financially or economically? Economically, if the process is stationary, that means as you keep on increasing lag length, these phi 1s, the magnitude of these phi 1s should become smaller and smaller and converge to 0. Intuitively, it should be the case because as you go further previously or past in time, the impact of events or shocks that have arrived in historically, they should die away gradually over time as time passes. And this is what exactly we mean by this stationary condition. More importantly, that also means that none of these phi's should be equal to 1 or greater than 1. If they are greater than 1, then not only shock increases, but it explodes. If it is equal to 1, that means even though it does not explode, but it does not die away infinitely ahead in the future, which is not possible in economics and finance or in general in any case. So we say that if this process is non-stationary or this sequence is non-stationary, then this process is not feasible to model. So in general, we rely on this characteristic equation and find its roots. This characteristic equation, we find its roots and we say if the roots lie outside the unit circle, then the process is stationary. That means if the roots of this equation, think of this as a polynomial, and the root of this equation are greater than 0, then this process is stationary. What essentially mean? Think of one of the root as maybe z1 or z2 and so on, some of the roots, and if I put those roots 1 minus phi 1 z equal to 0, then essentially z equal to 1 upon phi 1, which means this is just a simple, very simplistic example. We'll have a numerical example following in the following discussions in next set of videos, but just think of it. If this z value, if this z value is greater than 1, then only the phi 1 will be less than 1 in magnitude. But if this z value in terms of magnitude is inside the unit circle, that means either 1 or less than it, then phi 1 will become greater than 1 or equal to 1, which leads to non-stationarity, and this is what not desirable. So this is the property of non-stationarity, which is a non-desirable property. And to summarize, we expect the roots of this characteristic equation. This is the characteristic equation of an ARP process. We expect the root of this equation to be outside unit circle to the process to become stationary. That means if the process is stationary, then all the autocorrelation coefficients, first they will be smaller and smaller and converge to 0 as we go ahead past in time. That means phi p will be, in terms of magnitude, will be very small. And second, none of these autocorrelation coefficients should be either equal to 1 or greater than 1. None of them should be like that, as long as the process is stationary, which means all the characteristic roots of this equation lie outside the unit circle. Now that we have understood the theory behind the stationarity of an AR process, let us try to work out a simple example. Let us consider a simple AR process like yt equal to yt minus 1 plus mu t. Essentially, this process has a mean of equal to 0. As we said, in general, we'll take the mean as 0. And also, it is only affected by its immediate previous lag. That means only the immediate previous term in the series yt minus 1, yt minus 2. So for example, yt minus 1 will affect yt minus 2 will affect yt minus 1, but none of the second lag yt minus 3 will have no relation with yt minus 1, or yt minus 2 will not affect yt. So for this kind of process, recall, we can write yt minus 1 as L of yt, and we can put it in a more compact lag notation as 1 minus L yt equal to mu t. Now with Volt's theorem, we have the characteristic equation as 1 minus L, or its algebraic or polynomial notation as 1 minus Z equal to 0. Solving for this equation, we get Z equal to 1, which indicates that there is only one characteristic root which is equal to 1 or lies on the unit circle. Recall, the implication of Z equal to 1 means that one of the autocorrelation, there is only one autocorrelation which is equal to 1, indicating a process which is non-stationary or having what we call as unit root because its root equal to 1. Although even without doing this calculation, you could have already seen that the autocorrelation here is directly 1, which is not desirable. Why? Because autocorrelation of 1 means that whatever shock that has arrived or was there in the series yt1 minus 1, it will never die away. As process progresses, it will always, let's say there is a shock of magnitude m, it will always have a multiple of m. So in second series m square, m cube, so the shock will keep on multiplying every time further, and it will not die away. The shock will always persist with the power of 1 into 1. So the shock will never die away and it will always persist. Now, and therefore the process is non-stationary, and its inverse is also not possible, because the inverse would not be possible as per the Volt's theorem, if you recall what we said as phi L inverse, which essentially in this case is 1 upon 1 minus L, and the characteristic root being 1, this is not defined. So, and therefore this process is not a stationary process. It has a unit root, which is exactly, that is Z equal to 1, or indicating then process where the shocks do not die away. Moreover, the unconditional mean of an AR process is given by this expression below. Unconditional mean you can think of as a long-term mean. If there is no shock to process and we keep on moving ahead in future without any shock, in the long term, the process mean will converge to this. Although in the case of financial economics, this is not a very relevant or important result for us. Why? Because in general, we tend to assume this mu, or the mean of the process, as 0. So in that case, whatever the shocks may be, the unconditional mean in long term will always be 0 by the simple property this mu is already considered as 0. But still, it is important to note that there exists some kind of unconditional mean. In general, if we go outside the financial economics region, in general in economics, an unconditional mean is something which is called long-term mean. So if we keep on projecting the process and there are no new information incorporated, in the long term the process converges, the projections or forecast from the process will converge to its unconditional or long-term mean, which is a desirable property. However, like I said, in our case, financial economics, this mu is equal to 0. The mean is said to be 0, and therefore this long-term unconditional mean also becomes 0. Now, in case of, let's say, this AR1 process, let's say this, while we are not putting this mu equal to 0 and there is only one autocorrelation which is phi1, please recall this expression will become mu upon 1 minus phi1 by the Volt's theorem. So recall the our expression is phi L would be 1 minus phi1, and essentially when you take the inverse, this 1 minus phi1 will phi inverse will be 1 upon 1 minus phi1. Now in this case, as long as this phi1, if you recall, if this, as long as this is less than 1 in terms of magnitude, then this process is stationary. But as soon as this phi1 becomes 1, which means the autocorrelation is 1, this process becomes non-stationary, as we saw in the previous example. Also, if it is more than 1, then also this inverse is not possible. The Volt's theorem will not result in this kind of inverse, and again the process will not be stationary. For this process to be stationary, this phi1 has to be less than 1 in terms of magnitude. Then only the characteristic root of this equation, which is 1 minus phi1 z, will be available. That means they will not be 1. For example, if phi1 1, then characteristic root equal to 1, or if phi1 is, let's say, more, phi1 is greater than 1, then z will be less than 1. That means again the root of this characteristic equation will be either on the unit circle or inside it, which leads to non-stationary process. So to summarize, in this video we discussed what, and with a simple example, what would be the implication of non-stationarity of an AR process, and how do we model an AR process and convert it into a more amenable form like this and this. We also saw with the simple AR1 process how to convert into, through Volt's theorem, convert into a polynomial and obtain its characteristic equation, and then once the characteristic equation is available through simple programs, even with a calculator or a simple program, you can obtain its characteristic root. And as long as those characteristic root lie outside the circle, the process is stationary. However, if the characteristic root lie on the circle or inside the circle, the process is non-stationary. What is the implication of characteristic root lying inside the circle or on the circle? It means that either the autocorrelation is equal to 1, which means shocks to the series will not die away, or if it is inside 1, then they not only not die away, but they explode, which is not a desirable or feasible property in finance and economics. In this video, we'll again introduce the autocorrelation coefficient and its role in identifying the structure of a time series process. If we recall, the basic expression for autocovariance for a time series process yt at lag s was expectation of yt minus expectation of yt into yt plus s minus expectation of yt plus s, which is denoted as gamma s. This gamma s is autocovariance at different lags of 0, 1, 2 and so on. When this s equal to 0, the autocovariance at lag 0 is obtained, which is simply nothing but the variance of yt itself, which can be denoted as gamma naught. One problem with these autocovariances is that they have different units of measurement if you are measuring the different process, and therefore it is difficult to compare and interpret them directly because of this scale issue. And therefore a good way is to scale or standardize them with the variance gamma naught. So if you believe the process has a constant variance, that is gamma naught, which is nothing but the autocovariance of a process with its self, that is yt at s equal to 0, which means this will also become yt. This becomes variance term, and assuming if for a process variance is constant, that is gamma naught, if I divide any autocovariance gamma s with gamma naught, it is called autocorrelation measure tau s, as we have seen earlier. Now this tau s has a very interesting property that it lies between -1 to +1, where -1 means completely opposite movement, opposite lockstep movement, while +1 means completely in one direction. Generally in life, in practical scenarios, the number will be somewhere in between. Now, what is the importance here? Before we explain the importance, one thing you noted, as s equal to 0, tau s becomes tau 0, which is nothing but gamma naught upon gamma naught equal to 1. So the autocorrelation of a process with itself contemporaneous term is 1. Now, generally for a white noise process, and assuming, and recall we said that we generally tend to assume that it's a normally distributed white noise process. So a white noise IID process with a normal distribution, which has no autocorrelation structure. If you simulate the autocorrelations tau s, they are approximately, that means in large numbers, if there are large number of observations asymptotically, they are normally distributed. So for a white noise normal IID process, the autocorrelation themselves will be asymptotically, that means with large number of observations are approximately normally distributed with a mean of 0 and a variance of 1 upon t. That means if we plot it, it will appear something like a normal distribution, a bell-shaped curve with a mean 0 and a variance of 1 by t. Now, with using this property, we can set up a confidence interval for any such process where we want to establish what is, whether there is some autocorrelation structure or not. So for example, if you believe that a process is a white noise process and you plot it on a standardized normal distribution, which is nothing but a standardized version of normal distribution, its mean will be equal to 0 again. And now with 95% confidence interval, which is nothing but almost 2 standard deviation, on normal distribution at this point will appear at z equal to 1.96 and this is plus 1.96, and on a absolute simple normal distribution this will be minus 1.96 into sigma, which is 1 upon root t. Variance is 1 upon t, so standard deviation is 1 upon root t. Similarly, this upper limit of that 95% confidence interval will be plus 1.96 into 1 upon root t. So we can set up this confidence interval, and if there is no, I repeat, if there is no discernible structure, there is no autocorrelation, then the 95% confidence interval will be this. And if your observed sample correlation is beyond this range, that means either on the left side of the rejection region or on the right side of the rejection region, then you can with 95% confidence say that there is indeed some kind of autocorrelation in the process. Similarly, you can set up 99% or any other confidence interval using the corresponding Z values. So in summary, we are saying that as long as we are setting this 95% confidence interval with the assumption that process is a white noise IID process, that means there is no discernible structure, you can reject the null if your sample autocorrelation tau s lies outside this region for a given lag s, and that would indicate the rejection of null hypothesis. That means if the correlation is outside this region and you are able to reject the null, which would suggest acceptance of alternate HA, in general we call alternate as HA hypothesis, that there is indeed a significant, I repeat, significant or what we call as non-zero coefficient at lag S. Now whether that coefficient is positive or negative, that will depend whether you reject in this tail or the right tail. If it is rejection in right tail, then probably it is positive, non-zero positive. If it is on the left tail, then it is non-zero negative. Now there are two advancements in this statistic. One is called Box-Pierce test statistic, which is Q equal to T, which is the sample size, into tau k squares, the summation of all the correlation coefficient squares, and LB test, Lung-Box test, which is called Q star static, which is nothing but T into T plus 2 and then tau k square summation upon T minus K, where tau k is your autocorrelation coefficient at lag K. Now, these two are slightly different from the previous hypothesis or confidence interval estimation of autocorrelation coefficient. In the previous case, we were testing autocorrelation coefficient at different lags individually. These are joint tests of autocorrelation coefficient. That means when I run this test for Q or Q star, essentially I'm testing that up to the lag K, up to this lag K, all the coefficients are jointly equal to 0. I repeat, the null hypothesis here is that all the coefficients up till lag K are 0. The rejection of null, that is acceptance of HA, will indicate that at least one of them is significant. So these are slightly more powerful tests. The statistics are asymptotically distributed as a chi-square statistic. So you pick up the relevant values from the chi-square, this chi-square table, and compare them with the Q and Q star, and depending upon whether Q and Q star are higher or lower than these statistics, you reject or accept the null. So we'll see some of the examples in next set of videos. Notice if T is sufficiently large, then both of these statistics, they converge towards the same value. That means Q star and Q tends to become same. They converge towards each other when T is very large and increases towards infinity. Now, to summarize, what is the application or important role of this autocorrelation coefficient? The idea here is that the good idea here is that when you model any process, any time series process through models such as ARIMA model and extract the residual out of it, muties, those residual, you tend to assume as a null hypothesis that these residuals are normally distributed. They are like a white noise process with a normal IID distribution, that means independent and identically distributed with a normal distribution. However, then you apply these kind of null with either individual hypothesis test that we did in the previous discussion, or now with Q and Q star statistic, and you are able to reject the null that there is no autocorrelation. Then you have to conclude that there is some autocorrelation structure, and then probably your modeling of process was not a very good fit. And that is the whole point of it, to find this autocorrelation structure in the process, whether there is some discernible structure and your error terms indeed are not white noise. If they are not white noise, then the model that you have fit to, you model original process YT, because YT was your original process which you fitted with some kind of ARIMA or some model to obtain these error terms. That original model parameters were not very appropriate, or model itself was not very well specified, and you need to relook at your modeling exercise. That is the conclusion with this. So to summarize this video, we have introduced again autocorrelation coefficient, and we also saw their application in modeling time series processes. Please note, when you plot these autocorrelation coefficient on x-axis with different labs s equal to 0, 1, 2 and so on, this kind of diagram is called autocorrelation function, or ACF, or correlogram when you plot it visually across lags. Now that we have understood the theoretical underpinnings of autocorrelation coefficient, we'll try to explain its working and application with the help of a simple example. Consider a simple experiment or examination of a process YT where you have 100 observations, and at lags 1, 2, 3, 4, 5 you observe the following correlation coefficients. First order coefficient tau 1 as 0.207, tau 2 as minus 0.013, tau 3 as 0.086, tau 4 as 0.005 and tau 5 as minus 0.022. You want to test first individually whether these correlations are indeed statistically significant, that means non-zero, by that confidence interval approach. That is, this setting up this 95% confidence interval and checking each of the correlation coefficients individually whether they are non-zero and statistically significant. And the second, joint test or joint hypothesis approach with box PS BP and Lung box LB test to conduct the joint hypothesis whether all of them together are significantly or non-significant or equal to 0. Let us start with the simple 95% confidence interval approach, where we would like to set up a plus minus 1.96 into 1 upon under root t confidence interval like this. So you want to set up a confidence interval like this upon under root t and plus 1.96 upon under root t, and want to test whether each of the coefficient lie outside or inside this range. Because t here is 100, this number works out to plus minus 1.96 upon 10, which is minus 0.196 to 0.196. So this range is minus 0.196 and this range is 0.196. Now if we compare our coefficients individually one by one, let's see. So by that logic, this coefficient 0.201 is significant, this is not significant, this is not significant, this is not significant, and this is not significant. So that means only one autocorrelation coefficient at lag 1 is significant and non-zero, and this is positive also. So this is what we conclude from the first test. Let's look at the joint test. In the joint test, our null hypothesis is that all of them, tau 1, tau 2, tau 3, tau 4 and tau 5, all of them are jointly equal to 0. And now we would like to compute the statistics respectively Q and Q star with these formulas. T here is 100, all the tau k's are given, tau 1, tau 2 and tau 3, tau 4, tau 5 are given to us, and it is given to us that statistics corresponding to 5% significance or alternatively 95% confidence level is 11.1, and at 1% significance, that is 99% confidence, is 15.1. So let us work out the numbers. So if I compute the box PS statistic, that is T into summation of all the squares of autocorrelation coefficients, T is 100 and all the individual coefficients are shown here, their squares are added up, we get a value of 5.09. Similarly, Lung box or LB statistic is also given to us, which is 100 t into t plus 2, and into that formula tau k square upon k minus 1 k minus t minus 1 t minus 2 and so on up till t minus k works out to 5.26. Now if you recall our statistics at 5% and 1% level, none of them are significant. That means whether I compare with 5% or 1%, both the statistics are insignificant. What do we conclude here? In both cases, with the help of joint null hypothesis that all of them are zero, we fail to reject the null. That means we do not accept the alternate, and we conclude that all the coefficients are equal to zero, cannot be rejected. So we have to take them together as non-zero. However, this is in contrast with the first confidence interval approach, where the first coefficient of 0.206 appeared to be significant individually, while others were non-significant. So why this kind of contrasting result? So to summarize or conclude, here what is happening is that at lag 1, the coefficient is pretty large, it's 0.206, which is significantly different from 0. However, when we conduct the joint hypothesis, that means all of them, whether all of them are equal to 0, given the small magnitude of these tests, that for example tau 2, tau 3 and so on, these are so small that the overall power of joint test is decreased because of the smaller coefficient, and they go in favor of null. I repeat, because of the small magnitude of these coefficient, the overall power of test is pretty low, and we have to conclude, when we conduct the joint hypothesis, we have to go ahead with the null that all of them are together equal to 0. But when we examine them individually, clearly the first lag autocorrelation coefficient is pretty large, and we have to conclude that this process has a significant first order autocorrelation. So for example, if you try to put this process on some kind of AR process, it will be an AR1 process. It will be an AR1 process with this kind of structure into yt minus 1 plus our error term. Now here mu is almost 0. We'll consider mu to be 0, and this kind of process will appear. Mu is this is error term, which is generally a white noise process. So you can consider this error term, and the process will appear like this. In this video, we'll introduce autocorrelation function and partial autocorrelation function and understand them with the help of AR process, and how to differentiate AR process with the help of ACF and PACF diagrams. To begin with, we have already understood that autocorrelation function or correlogram is a plot of these autocorrelations across different lags starting from 0, 1, 2 and so on, and that this autocorrelation function at lag 0 takes a value 1, and then subsequent lags it takes different values. However, the problem is that because the process is correlated, for example, there is some kind of correlation between yt and yt minus 1, even if there is a single order correlation, that is some correlation phi between yt and yt minus 1 and yt and yt minus 1 and yt minus 2, there is a spurious correlation. Mathematically, there is a spurious correlation that results between yt and yt minus 2, which is smaller than phi, somewhere around phi into phi, closer to phi square, driven by the fact that there is a correlation between yt and yt minus 1 and yt minus 1 and yt minus 2. So closer to phi square kind of correlation appears between yt and yt minus 2, and phi cube between yt and yt minus 3, and so on. And therefore, if I want to know the exact autocorrelation structure, I need to go with something called PACF, partial autocorrelation function, which accounts or sort of accounts for this spurious autocorrelation and gives me a pure correlation, pure autocorrelation across different terms, let's say phi t to yt minus 2 or yt to yt minus 3. Now, how does an AR process figure on these ACF and PACF grams? Conceptually, when you have a autocorrelation structure, the AR process has a geometrically decaying ACF. I repeat, AR process has a geometrically decaying ACF because of that spurious correlation. However, the PACF process accounts for this spurious correlation and only shows the exact autocorrelation structure that is present, and therefore on PACF diagram you have non-zero points only equal to AR order. For example, if your actual autocorrelation structure is of 2 lag, that is with lag 1 and lag 2, then PACF will have 2 non-zero points at lag 1 and 2, and rest of all will have 0 values. Let's look at how it appears. We have a simple AR1 process with first order autocorrelation of 0.9. So the dark blue bars are ACF, and notice it takes a value of 0.9 at first lag, but second lag it is closer to 0.81 and then 0.89 cube and so on. So kind of exponentially declining structure with ACF diagram. As we discussed, so these rest of these, the first autocorrelation is correct, but rest of them are spurious. So how PACF accounts for it? Let's look at the lighter blue diagram, lighter blue bar, which is PACF. The first bar at first lag is exactly identical as the ACF diagram, but then it is cut off there itself. Then there are no lags. So that means PACF diagram clearly helps us identify that this is a first order autocorrelation structure. Similarly, look at this AR1 process where first order autocorrelation is 0.5. Again, the first lag at lag 1, we have ACF and PACF values are non-zero and same as 0.5, but then ACF exponentially declines while PACF, the values are straight away cut off to 0. So in this fashion, PACF helps us in identifying AR process. Please note that if there were two AR terms, they will be appearing on PACF process in the form of two bars and so on for 3, 4 and more autocorrelation structure. But on ACF, they appear as exponentially declining bars. Let's look at another two diagrams. Interestingly, in this we have AR1 process with a negative autocorrelation structure. So first at lag 1 we have a value of minus 0.5, which is same for PACF and ACF both, this PACF and ACF. However, after that you notice that it takes minus 0.5 to the power 2, which is close to 0.25, and therefore magnitude exponentially declining, but sign is continuously changing with the power of minus 0.5 to the power n, depending upon n first, 1, 2, 3 and so on. This value, the bar is positive or negative, but on PACF there is only one bar, which is first lag minus 0.5. Again, PACF helps us in identifying the AR process, its lag structure. If you look at a non-stationary process, notice this is a non-stationary process because here the autocorrelation coefficient is 1. So it is on the unit root circle. And notice on ACF diagram, because of this property that shocks are not declining, it's a non-stationary process and shocks are not decaying. On ACF diagram, we have continuously all the bars at 1, including 1, 2, 3 and all the subsequent lags. However, again on PACF, the bar is only non-zero and takes a value of 1 at first lag and then it is cut off. So this identifies the process non-stationary because now the ACF bars are non-declining, they are constant, which shows non-decay. There's no decay of shock, which is sort of indication of a non-stationary process. But PACF, again we can identify that non-stationarity appears at first lag with the order of 1. So to conclude and summarize, in this video we saw how with the help of ACF and PACF process we can identify AR process. So when we look at AR process, its ACF is geometrically declining for a stationary process and PACF has exactly non-zero lags which are same as the order of the process, AR process. In this video, we'll introduce another very important class of time series processes called moving average processes or MA processes. This form that in ARIMA model, that MA component, moving average process, a very important component of ARIMA model. Let us introduce the model and concept behind the MA process. Think of a financial time series process YT such as security market returns as a linear combination of error terms or white noise processes called mu-t. So here the concept or idea behind this process YT is that it is simply a linear combination of these white noise, the current white noise terms mu-t and historical white noise term mu-t minus 1. So what are these mu-t's? Conceptually, these mu-t's are like information shocks that have arrived in the process at time t. Think of day t, let's think t in terms of days, and any sentiment or information shock that has arrived on day is modeled as mu-t. Now, a white noise process mu-t with a sort of zero mean, that is expected value of mu-t as 0, and a constant variance sigma square, the variance of mu-t as sigma square, are employed to model this mu-t term. Generally, it is believed that information that is arriving has no connection with its own self previously or historically. For example, the information that has arrived today probably may have no relation with information that has arrived tomorrow or yesterday. That is one assumption which leads us to employ white noise processes, a very important assumption. And second, we also assume there is no discernible structure. So the correlation terms across mu t's, mu t minus 1 and so on up till mu t minus k, there is no discernible autocorrelation structure, and that leads us to model this mu t process simply with the white noise as a white noise process. Now please note, while we are assuming as it as a white noise process, in financial and economic terms, this mutis for us is some kind of information shock that has arrived on date t, and we tend to assume it to be a closer associate of a white noise process. Now let's again go back to our MA model of process YT, which is a linear combination of these mutis, current shock mu t and historical shocks mu t minus 1. Mu here is the average, some kind of average value or constant value. For practical modeling purposes, later on we'll consider this mu as 0. So this constant term is 0. Let's take 30 seconds to understand what this constant mean is. This constant mean for a process like security market return is average return, average year, average period by period return. Now, if you're talking about financial market and a stock gives you a fixed abnormal extra average period by period returns, that sort of violates the concept of market efficiency, and therefore for all practical purposes this number should be very close, insignificantly different from 0, and therefore we may take it as 0, and that will help us ease the mathematical modeling part of the process as well. So let's begin this assumption that this mu is very close to 0, and all we are interested in is modeling these current and historical shocks or white noise processes, mu t minus 1 and so on, and theta 1, theta 2, these thetas being the correlate sort of coefficients of these shocks. Now we can again put it in a sigma in a more compact manner with the help of lag operator. What is a lag operator here? So again, as we discussed, a lag operator is something Li of yt process is nothing but yt minus I at ith lag. So if I'm writing Li of mu t, it is like mu t minus I. So this is often referred to as either lag operator or backshift operator. So we can start from this notation to a more compact sigma notation like this, where sigma equal to 1 to q theta I into mu ti minus 1, where I runs from 1 to q, and later on we can apply a lag operator, a lag function of theta, like theta L mu t, where theta L is nothing but 1 plus theta 1 L for plus theta 2 L square and so on up till theta q L q. Now these algebraically, this polynomial, this can be considered as a polynomial. For example, second lag L2 with Volt's theorem can be taken as L square, and we'll make use of it algebraically. And please recall, in our previous videos, we said for AR process, this was characteristic equation for the AR process. In that case, here we'll consider it as a characteristic equation of moving average process. Last, another very important point, while modeling this, we have taken mu t's to be white noise IID terms that are distributed with a zero mean and constant variance. For ease of modeling, we take the distribution at which they are distributed as normal. So this IID, or independently identically distributed mu t's, are taken as normally distributed. And to summarize, a moving average model is simply a linear combination of these white noise mu t's processes of at current time and historical times. Once we have finalized these assumptions about the MA process, we can derive certain useful results. So look at this mu t process or time series MA Q order process. So these mu t's run up till time like Q. This is considered as an MA process of order Q. There are some desirable results. The expected value or the mean or this process is mu. Again, this will become 0 for us while later on when we are modeling these results. But still, theoretically, this value is mu. But in financial markets, this will be taken as close to 0. The variance of mu t is this constant number, which is a function of the variance of sigma square, which is the variance of mu t itself, and summation of these theta 1 square, theta 2 square, which is nothing but the coefficient of these mu t's. So this is a constant value driven by this expression. This is also called gamma naught, the variance term. What about auto covariances? So this was variance. Auto covariances are also given by this expression. As we can see, theta s plus 1 into theta 1 and so on. And then a multiplication with variance of the sigma square. What is the sigma square here? This is the variance of mu t. We assumed a constant variance of mu t white noise processes. These white noise processes are constant variance for different lags t, t minus 1 and so on as sigma square. So this is also same as, this is one critical assumption, slightly it may change. So there's nothing that holds, forces this assumption to hold. It's just a simplifying assumption to make modeling easy. And also please notice, these autocovariances will exist maximum up to order q. So because we have considered an MA process of order q, these autocovariance structure will start from lag 1 and up till lag q. So the qth lag will be the last lag by which autocovariance will exist. After any lag higher than lag q, autocovariances will be 0. So to summarize these notation, what we can call about this MA process, how we can summarize this MA process, as for a MA q order process, it has a constant mean mu, a constant variance, this one, which also depends how many, what is the order of the process theta q, and auto covariances that are non-zero up to lag q and 0 thereafter. So up till lag q they are there and 0 after that. So now we have understood the concept and mathematical model behind the MA process. In next set of videos, we'll try to work out some of these MA process with the help of simple examples. In this video, we'll understand the MA process modeling with the help of a simple MA2 order process. Let us define a simple MA2 order process like this. Yt as a combination of white noise processes mu t minus 1, mu t minus 2. These are the two previous period shocks. That's why second order process, MA2 order process. And theta 1, theta 2 are the coefficients of this white noise process, where expected value of mu t equal to expected value of mu t minus 1 and so on, expected value of mu t minus 2 equal to 0. So it has 0 expected value, and its variance of mu t is equal to variance of mu t minus 1 equal to variance of mu t minus 2 equal to sigma square. So this is assumption about white noise process, and we take it to be a normal, some kind of normal white noise process. So what is the expected value or unconditional, some kind of mean of Yt as expected value of this expression, which is nothing but this. Now expectation operator runs on stochastic variable like mu t. For constant, it is for example, expected value of theta 1 would be theta 1 itself because it's a constant term. So we apply expectation operator one by one. So expectations of mu t plus theta 1 times expectation of mu t minus 1 plus theta 2 times expectations of mu t minus 2. But these expectations are nothing but 0, because we already said we have assumed this is as a white noise process with a 0 mean. And recall, for Yt itself, we are using that constant term mu as 0. Like I said earlier in the previous videos, we'll take that constant mu as 0, which that's why I have not put that mu in that MA process here, the mean term or constant term, and remaining all these mu t's, their expectations are 0. So we get the expected value of Yt as 0. This is our generic expression for white noise processes with MA2 order Yt, its expectation is 0. Let's come to the variance part of Yt. Now variance of Yt, the generic expression is expected value of Yt minus expectation of Yt into Yt minus expectation of Yt, because this is a variance part. Now please note, expected value of Yt is already 0 that we have defined here. So we'll simply substitute this for 0 and we get expected value of Yt into Yt, which is expected value of Yt square. And we can now put Yt, we can substitute this value of Yt here and here. If you focus on this expression, you would notice that there would be some square terms. When mu t gets multiplied with mu t, you will get mu t square, or mu t minus 1 multiplies with mu t minus 1, you'll have theta 1 square mu t minus 1 square, and similarly you'll have theta 2 square mu t minus 2 square. But then there'll be some cross product terms when mu t gets multiplied by mu t minus 1. However, and the catch-all expression for these cross product terms is this. And if you recall, we said that this mu t is a sort of white noise processes. So therefore, any correlation between mu t and its previous lag, like mu t minus k, for k equal to 1, 2, 3 and so on, will be 0. So what I'm essentially saying is that correlation or expected value of mu t into any mu t minus k, this can be mu t minus 1 or mu t minus 2, all these terms, the catch-all expression will be 0 with a simple financial logic. And here financial economics dominates over mathematics. that there is no correlation, there is no discernible structure or correlation across mu t's across different time periods, and therefore the catch-all expression for this term is 0. And we are left with expected value of mu t square as this part only. So the remaining for all the cross products, the expectation is the expected value of mu t into mu t minus 1 is nothing but covariance of mu t and mu t minus s, which is 0. Why? Because we said that mu t's are white noise processes with no discernible structure and therefore no auto correlation or covariance. And therefore all we are left with this expression. But here we also said that this expectation of mu t square is by definition nothing but covariance of mu t. This covariance of mu t comma mu t is nothing but variance of mu t, and which is same as sigma square. So we have already defined that expectation of mu t into mu t is nothing but covariance of mu t with mu t itself, which is nothing but variance of mu t, which is equal to sigma square. And whether now it is mu t minus 1, variance of mu t minus 1, or mu t minus 2, all of them are sigma square. So with this logic, we are left with this expression, and knowing that this is sigma square, this is also sigma square, and so on, we can take this sigma square common. And because theta 1 square, theta 2 square are constants, their expectation, for example, expectation of theta 1 is same as theta 1, and expectation of theta 1 square is also theta 1 square, and likewise for theta 2, and so on. So this expression, that is variance of yt, is nothing but 1 plus theta 1 square plus theta 2 square into sigma square. This is simply because this is a MA2 order process up till theta 2 only. So we have up till theta 2. If there was a generic term theta k, as we saw in the previous videos, it will go up to theta k square. So now we have obtained the expressions for expected value of yt, which is 0, with the assumption that this process yt itself has no constant mu term, which we assume to be 0, and therefore our modeling part has become much easier with the expected value of this MA2 order process as 0. First very important result. And second very important result, the variance of this process is 1 plus theta 1 square plus theta 2 square into sigma square. So the variance term is also dependent on these coefficients theta 1, theta 2, and the variance of this white noise process mu t, which is sigma square. So now that we have understood the variance and expected value of this MA2 order process, in the next video we'll look at its autocovariance. In this video, we'll try to understand the autocorrelation structure of MA2 process. Recall, in the previous video, we have tried to compute the variance of an MA2 process, this kind of process. In this process, we had considered a constant mean, which is 0, and these two terms define this MA2 nature of the process. Now, for this process, let's start with the basic definition of autocovariance at lag 1. So that is expected value of yt minus expected value of yt into yt minus 1 minus expected value of yt minus 1. We have already said in the previous video that expected value of yt is same as yt minus 1 and so on for 0 for this particular given process, and therefore these terms will become 0. So we are left with expected value of yt into yt minus 1. Now again substituting for yt this expression, and for yt minus 1, which is just 1 lag previous, so we'll have, instead of mu t, we'll have mu t minus 1, instead of mu t minus 1, we'll have mu t minus 2, and so on up till mu t minus 3. Now if you recall, the multiplication of mu t into mu t minus 1 or mu t minus 1 with mu t minus 2 and so on will lead to cross product terms, while multiplication of mu t with self, in this case there is no mu t, so we have mu t minus 1 into mu t minus 1 leads to square terms. If you recall from the previous video, given that these mu t are white noise process with no autocovariance, all such cross product terms, the catch-all expression for all such cross product terms is 0, and only those terms that are variance, that is mu t minus 1 into mu t minus 1 or mu t minus 2 into mu t minus 2. So mu t minus square minus 1 and mu t minus 2 square will remain. Their coefficients are easily determined. For example, mu t square minus 1 is a combination of this and this, so it's theta 1. Mu t minus 2 will have theta 1, theta 2, and so on. So this is the expression for autocovariance gamma 1. Or we already know that expected value of variance of mu t minus 1 and mu t minus 2 is same as sigma square, so we can take that out. So this is the expression for autocovariance at level 1. What about level 2? So for level 2, this t minus 1 will become t minus 2, t minus 3, and t minus 4, and now only these two terms will survive. So we'll have theta 2 times sigma square. All the other terms are cross products like, for example, mu t minus 1 and mu t minus 2, mu t minus 2 with mu t minus 3 and so on. So this is gamma 2. If we move anything ahead, if we move any further than second lag, notice this will become mu t minus 3, and therefore, and this mu t minus 4 and mu t minus 5. So all the products will become cross products. There will be no variance terms, and therefore the value for gamma 3 or autocore variance at lag 3 is 0. What is causing this? This is precisely driven by the nature of this process, which is MA2 process, because there is no theta 3 corresponding to mu t minus 3. This is only two second order process. The third variance, the auto covariance at third level is 0. So we are restricted for auto covariances at level 2. Similarly, had it been an MA3 process, there would have been term for gamma 3, that is auto covariance at third lag, but no fourth lag and onwards. In the next step, we'll compute the auto correlation function ACF or taus. So these tau i's are nothing but auto covariances divided by variance terms. Variance terms we have already calculated in the previous expression as this. For this process, this was our variance term. So let's start with tau naught. Tau naught, as we already know, is nothing but gamma naught divided by gamma naught, that is variance divided by variance, and it is 1. So irrespective of the process, this will always be 1. But what about tau 1? Tau 1 is gamma 1, which is auto covariance at lag 1, which we have computed in the previous slide like this, and gamma naught we have already computed in the previous video like this. So this will cancel each other out, and we are left with this, which is tau 1. Similarly, I can calculate tau 2, which is gamma s upon gamma naught, which is this expression. There is no tau 3. Tau 3 is equal to 0 because precisely this was MA2 process, and any further correlations would be 0. So to summarize, in this video, we understood how to compute autocovariance, and with those autocovariances, dividing them by variances, how to compute autocorrelation functions tau naught, tau 1, tau 2 for this MA2 process. We also noted, because this was MA2 process, any higher order autocorrelations and covariances would be 0 because the process is restricted to second order lag of mu t's. In this video, we'll try to understand the autocorrelation function and partial autocorrelation function, that is ACF-PACF plots for an MA process, and differentiate it with AR process. To begin with, recall in the previous video, we said that MA process has an autocorrelation function or ACF, which is exactly the number of autocorrelations or the number of white noise terms, the order of MA process, which is same as order of MA process. So the number of autocorrelation terms tau i's will be significant, which is equal to exactly the MA order. In the previous case, it was second order process, so we had autocorrelation functions tau i's significant up to second order. So that clearly explains that when we'll examine the ACF, it will be the number of ACF or autocorrelations will be same as MA order. But what about PACF? Without going into the mathematical proof, theory suggests that an MA process can be transformed into infinite order AR process. I repeat, an MA process can be transformed into an infinite order AR process, and therefore when it is examined on the PACF plot, there will be infinite number of correlations for an MA process, and therefore when we examine ACF for the MA process, for example, look at this MA process, which is a simple first order MA process with the coefficient as minus 0.5 for the white noise mu t minus 1. So if you look at ACF, which is in dark blue, it is cutting off at the first level itself. Only there is one bar, which indicates that this is a first order MA1 process. However, if you look at PACF, their magnitude is exponentially declining. So the magnitude of PACF is exponentially declining through a reasonable number of large terms. So it's like exponentially declining. Similarly, if you look at this MA2 process, where one term is positive and other is negative, 0.5 and minus 0.5, we look at the dark blue has two specific, the ACF has specific 2 bars, while again the magnitude of PACF is exponentially declining in terms of graph, positive negative, which reflects this kind of structure, positive negative, but in terms of magnitude, the magnitude is exponentially declining. So this is how we interpret the ACF and PACF plots for MA process. If to summarize, if we contrast these ACF, PACF with the AR process, recall for AR process, the ACF diagram was exponentially declining, while PACF was exactly cutting off at the number of bars same as AR order of the process, ARQ then order Q. In contrast, for MA process, the number of ACF bars are exactly limited to MA order. So if it is MA P order process, the number of bars in a ACF diagram will be P. However, if you look at the PACF plots, they will be exponentially declining in terms of magnitude, because like I said, an MA process can be converted into infinite AR process, and PACF will represent that characteristic, that the number of lakhs will be exponentially declining. That infinite AR kind of process. Obviously, that infinite AR process has coefficients that are declining as we go ahead and pass. So this declining nature will be captured in the PACF. That infinite AR process will be captured with these PACF diagrams. So this is how we different and contrast between AR and MA process on ACF and PACF plots. To summarize, we noted that time series models offer an extremely simple and useful class of models. In particular, we noted that time series processes are effectively modeled with ARMA-RMA processes. However, any time series modeling requires a stationary data, that is a constant mean, constant variance, and autocovariance structure that is not changing across time. We also noted that a non-stationary property has a very undesirable property, that its estimation results in spurious relationships that do not exist. Then we introduced autoregressive or AR processes, which are a very important class or component of ARMA models. In the AR process, a time series is expected to be dependent on one or more of its own past values. An ARP process is said to have an order P, that is, the series is dependent on its own past P values. The strength of this relationship is defined by the autocorrelation coefficients of the process. Moreover, if the series is stationary, then these autocorrelation coefficients have a declining structure. That is, they tend towards zero as we go back in time. This is a desirable property as it indicates that the impact of distant terms is less in magnitude. A stationary AR process can be identified with the help of one exponentially declining ACF plot and two a PACF plot that has non-zero bars up till the order of AR process and no bars, that is zero, thereafter. An MA process is a linear combination of current and past white noise error terms. An MAQ process is said to have an order P if it is dependent on its P historical values. An MA process is said to be invertible if the coefficients of white noise terms have a declining structure as we move further down in past. Also, then it can be converted to an infinite AR process as well. A white noise process has no discernible structure, and MA process can be further identified with an exponentially declining PACF diagram and an ACF plot that has a non-zero bars up till the order of MA process and no bars, that is zero, thereafter.